So what we're going to do is we're going to look at some of the reactions that our alkanes, alkenes, and alkynes can undergo. So alkanes can undergo basically two reaction types, or two that we will look at least. The first is combustion, and the second is substitution. Now, we're familiar with combustion reactions because we know it's a rapid reaction of some fuel, in this case our alkane, alkene, or alkyne, with oxygen, and we get heat, light, and oxides. So for example, if I have my propane undergo combustion, it'll react with oxygen, I'll get carbon dioxide and water. Now, combustion reactions are the only reactions involving organic compounds that we have to worry about balancing. All of our other reactions that we do, we're not going to necessarily worry about balancing them. Okay? A second reaction that our alkanes can undergo is substitution. Now, our substitution reaction, what occurs is we replace one of our hydrogens on our alkane with an organic, with a halogen. So the halogens that we could replace it with, fluorine, chlorine, bromine, or iodine. Now, in this example, X indicates any alkane, or sorry, any halogen, and we can have it react with our alkane. And so in this case, we have our methane react with our halogen. We'll get what we call an acyl halide, and then a hydrogen halide. Now, one of the things that we have to watch out for is that this reaction requires energy, first of all. And it requires energy usually in the form of ultraviolet energy. Now, a second thing we have to watch out for is that when we have our halogen, we can replace more than one hydrogen. And so we can get more than one product. And the product and the ratio of the products that we get will depend on the amount of halogen that we supply, as well as our organic compound. And so for example here, if we have our same methane undergo a substitution reaction, as you can see, we can get multiple products being formed. Okay. Now, our alkenes and our alkynes, unlike our alkanes, can undergo a variety of different reactions. And that's because my double or triple bond is a reaction site. And so as a result, I can have a reaction where I break the double or triple bond. And we know from the previous unit that because they're pi bonds, the second bond, the electrons are above and below our bonding axis and they're exposed. So this will allow for a reaction to occur because I can get at those electrons. Okay. And so one type of reaction that we can do is what we call an addition reaction, where I take my alkene or alkyne, I add something to it, the double bond is broken, and part of the component that I add goes onto each of the carbons that was originally involved in a double bond. So we have a variety of different addition reactions that we can have our compound undergo. We can have it undergo a hydrohalogenation. This is basically where we add hydrogen to it. We can have it undergo what's called a halogenation, where we add a halogen. A hydrohalogenation, where we add a hydrogen halide, for example HCl, or a hydration reaction, where we add water. Now, the different reactions have different conditions for adding on different things, and so we're just going to go through them quickly. So hydration reaction, this is where we can add hydrogens to our alkenes or alkynes. The reaction requires a catalyst and a bit of heat, okay, and allows us to convert what's called an unsaturated hydrocarbon into a saturated one. So for example here, I can have my ethene react with my hydrogen, and it will give me ethane. In my halogenation, what happens is that I'm going to add a halogen, and I'll break my double bond. Now, because halogens themselves are more reactive, this reaction can occur at room temperature, and we don't require a catalyst. So here, I take my alkene, I add my halogen, and each of the atoms from the diatomic halogen will go onto each of the carbons involved in a double bond. Now, when we do our hydrohalogenation, this is where I add my hydrogen halide. One of the things that we have to do is we have to watch out for our alkene that we're adding it to, our alkyne. In that, if the two carbons involved are not the same, then I can get more than one product. And what we mean by not the same is if they have different types, or sorry, different numbers of hydrogens bonded to them. So when we look at this reaction that's going to take place, we can see that my carbon here on the end has 2 hydrogens, and my carbon here only has 1 hydrogen. So since the two carbons have different numbers of hydrogens bonded to them, that means that I can get more than one product. When this double bond breaks, my chlorine could go here, my halogen could go here, or my halogen could go here. And so therefore, we have to take into account Markovnikov's rule. Now, Markovnikov's rule says that when a hydrogen halide, or water, is added to our alkene or alkyne, then the carbon with the most hydrogens bonded to it is most likely to get the hydrogen, which means that the richer get richer. So if we take a look here and we're going to apply our Markovnikov's rule, okay, what we can see is that when my double bond is broken, this carbon here or this carbon here could get the hydrogen, and then the other one would get the halogen. So we could get a case where my halogen is on the second carbon in the chain or in the first. Now, since this carbon, my first carbon, already has 2 hydrogens, it's more likely to get the hydrogen. Since this carbon has fewer hydrogens, it's more likely to get the other part and not the hydrogen. And so as a result, what we would say is that we would say that this right here is my major product, and this is my minor product. Now, when we undergo a hydration reaction, this is where we add a water to our alkene or alkyne, and this requires the use of a catalyst. And again, if it's unbalanced, we have to take into account. So when we have our reaction take place, because it's unbalanced, we get 2 products, and we can see that this is our primary product because the second carbon in the chain only has 1 hydrogen, so it's more likely to get the hydroxide in the addition reaction. Okay, now we can have our aromatic hydrocarbons undergo addition reactions as well, and substitution reactions. So for example, if I have a cycloalkane, it can undergo a substitution reaction, but that requires UV light. If I have benzene, now benzene is a 6-carbon ring with 3 double bonds in it, so we usually draw it as a hexagon with a circle in it. If I have that react with a halogen, I usually require a catalyst of an iron halide. So if I was going to add chlorine to my benzene ring, then I would use iron 3 chloride. If I was going to add bromine, I'd use iron 3 bromide. And it will undergo a substitution reaction. And if I want to have an addition reaction with my cycloalkene with a halogen, it can occur at room temperature. Okay. Now, my aromatics can undergo addition as well, where I can add a NO2 group. And an NO2 group is referred to as a nitro group. And so I can have my benzene undergo the same reaction to get a nitrobenzene. And this reaction requires the catalyst of sulfuric acid as well. Okay. And we can also add our carbon chains to my benzene ring, and where I have a halide alkane, and we'll go into this in more detail, and I have that react with my benzene, and again I need the same catalyst as before. So if my if I had a halogen with chlorine on it, sorry, a carbon chain with chlorine on it, and I want to add the carbon chain to my benzene ring, then my catalyst would be an iron 3 chloride. So, for example, if I took my benzene and I want to add a methyl group to it. So here I have my halide alkane. I'm going to have my catalyst. And so my catalyst in this case will be iron 3 chloride, so that the halogen in the two spots match. And then what will happen is my methyl group will be attached to my benzene chain, and I'll get HCl as well produced.